Let's recall the basics of the particle in a box. Take, for example, a single electron. The energy eigenstates have the energies En equals h squared over 8ma squared times n squared. N squared is the quantum number, and it's either 1, 2, 3, or any other positive integer. The stationary states are described by the wave functions psi n equal to 2 over a times sine of n pi x over a, where a is the length of the box. Here's the energy level diagram. The lowest level is n equals 1, followed by n equals 2, and so on in ever-increasing spacings. This is all for a single particle in a box, say an electron. What if we have multiple electrons in the same box? In order to describe such a situation, we need to know two fundamental facts about electrons. The first fact is that electrons have spin. Spin is an intrinsic angular momentum. Visually, you can imagine the electron as a tiny ball that spins around itself. It can be either in a spin up or in a spin down state. Spin up looks like this, and it's called the alpha state. Spin down looks like this, and it's called the beta state. The overall state of an electron is described by the product of a spatial wave function with a function representing the spin state. The spatial state is one of the energy eigenfunctions, psi n. The spin state is either alpha or beta. So for example, the overall state would be psi 1 alpha or psi 7 beta. With this principle, we have to extend the energy level diagram. Each energy level is actually doubly degenerate. As an electron in a given spatial state can be either spin up, alpha, or spin down, beta. In this context, let's introduce a few terms that you will be familiar with from introductory chemistry. An orbital is a one-electron wave function. Specifically, only the spatial part of it. A spin orbital, on the other hand, is a one-electron wave function that includes the spatial and the spin part. For example, an orbital would be described by just a function psi 3. A spin orbital would be psi 3 alpha or psi 3 beta. If the orbital is in a molecule, it's called a molecular orbital, or MO. If the electron and the orbital are in an atom, on the other hand, it's called an atomic orbital. These are very important terms and concepts. The second fundamental fact about electrons is the Pauli exclusion principle. It states that two electrons are never in the same state. This is a fundamental principle of nature and it cannot be derived. It is consistent with all experiments though. Essentially, what it means is that if you have two electrons, their overall state wave functions must differ either in the spatial or in the spin part. They cannot have the same spatial and the same spin part. With these two principles, we can put multiple electrons into a one-dimensional box. Let's say we're interested in the ground state, the state of lowest overall energy. We will put in the electrons from the bottom up. The first electron goes into the psi1 alpha state. The next one goes into psi1 beta. It can't go into psi1 alpha, since then the first and the second electron would have the same state, which is forbidden according to the Pauli exclusion principle. So the second one goes into psi1 beta. In analogy, the third one goes into psi2 alpha, and the fourth one goes into psi2 beta, and so on. The highest occupied state in such a multi-electron system is called the highest occupied molecular orbital, or HOMO. The next state above, the lowest unoccupied orbital, is called the LUMO, for lowest unoccupied molecular orbital. We can promote an electron from one state to one of the empty states by the absorption of a photon that has the right amount of energy to bridge the gap. The most important of these transitions is from the HOMO to the LUMO. In this simple multi-electrons in a box model, you have to note one important thing. We are essentially treating the electrons as independent particles. None of the electrons is aware of the presence of the others. This is a very crude approximation, of course. Electrons are negatively charged. If you bring two electrons close to each other, they will repel each other. Due to this repulsion, the position of the two electrons is in reality correlated. In other words, if one electron is on the left of the box, the other one prefers to be on the right. The symptom model here completely neglects this electron correlation.